Okay, so we have some motors, and we're going to talk about gears and efficiency. So um, I've got this one motor here with no gear on it, and it's pretty easy to turn the motor shaft, no problem there. I've got this harmonical gear, wave strain gear. It's got a hole in the middle, and I'm going to try to turn the shaft. I can't, I can't turn the shaft back driving it. I mean, with enough torque you can. This is like 100-to-1 gear. Um, that's a hard one to back drive. And this one is a 10-to-1 gear ratio, and I can turn the output shaft and back drive the motor. So this is, of course, the most efficiency. There's no gear, and then 100-to-1. That's efficient, but it's still hard to back drive. So some energy must be lost in the gear. And then this gear, I'm not sure what kind of gear it is because there's no model description on it, so I can't tell. But it is a 10-to-1 gear. So we're going to talk about the efficiency of gears here. And I like this guy, Kevin Lynch. He does some great videos from Northwestern Robotics. But the idea is you're going to put some power in and you get some power out. And if your gear is infinitely efficient, 100% efficient, you're not going to lose any energy in the form of heat in the gear. And the output velocity divided by the input equals the input velocity divided by the gear, and torque is the gear times the torque in. So you put some torque in, you multiply it by, say, 10-to-1 or 10, or you go 10 times as slow. But the concept is efficiency, and this Greek n eta is a percentage. So you're going to get some, depending what you put in, times a percentage. The number is less than 1, so 1 would be ideal, 0.97 would be 97% efficient, and that would be all the same power out, and the formula applies to the speed. Its efficiency is less, or your speed and your torque would be less for a given set of power in. So the idea is for a given speed torque curve, you'll get different torque efficiencies and maybe require more voltage to go faster or more current to get more torque, but it's going to be lost in the gear in the form of heat. Some typical gears for the efficiency, a Spur gear, 90% worm gear, few stages, many stages. As you have more stages of gearing, of course you have less efficiency because every gear is a stage, then you lose efficiency through it. Other things too, like seals on the shaft, make things harder to turn, friction, things that affect your efficiency of what you're trying to deliver for power from the drive, trying to get to speed and torque at the output. Where does all the energy go, right? So I've made that mistake with a ball screw, and it needed like 10% more energy because it was only 90% efficient. Belts seem pretty efficient because it's just attached to the motor shaft. It's easy to turn the motor shaft. But back driving a gear with all those teeth and the grease or the oil that's in there. Now, some other gears that they didn't mention, Planetary Gear, supposedly 97%. That's probably per stage and like a good one or a very efficient one. Depending on your ratio and how much torque you're getting out of, you don't get something for nothing. So the more torque you're getting out, the more turns ratio or gear ratio, probably the less efficient. And that would probably be same applied to a cycloidal, which might be a little less efficient, or subjectively a little less efficient, but it's still pretty darn efficient. So these are good for a lot of the robotics where you're worried about the efficiency or saving energy on your battery, right? And this harmonic wave strain gear, 91% efficient. That may depend on your gear ratios again. And a ball screw, only 90% efficient. There was a formula for calculating on the ball screw. You got your force, torque becomes force, and there's the length of the lead or the pitch. So one rev of the motor, you're going to go a certain distance, and then the efficiency factor there, 0.9. And here's an example of the output and the input. So you lose torque. You just have to put more current in and apply more torque to the motor than you would get, coming out for force linearly. So that's a good example of the torques. And we're going to take a look at the different kinds of gears here just to get a feel for it. So this is a planetary, and you can see if the sun was in the middle, then in green here, the planets would be rotating around the sun. This outer part is not rotating, but what you do notice is the input shaft is turning slower than the output shaft. In this, it's back drivable. So maybe in this picture, you can see when the planets are stationary with respect to the sun, you get rotation on both the output shaft and the hub in it. Most of these pictures show the planets rotating around the Earth, but it can go either way. So this is typically used in car transmission for that fact of being able to drive things back and forth. Another one is cycloidal gear, and you can see there's a cam on the shaft here, and as it's rotating, it sort of walks its way around. So lots of fast turns on the motor shaft and slow turns at the output. This gives you your increase in torque and decrease in speed. This by itself would be wicked coggy, so they usually have a second dial here that these pegs go through with an offset cam, so that it counters the vibration that you get once per rev of the motor shaft. So these are usually doubled up from what I've seen. And this is the harmonic gear, the wave strain gear. And so as the inner shaft is rotating quickly, the outer shaft would be rotating more slowly. I don't think that's such a great image of it. But the takeaway on this was efficiency. So we're concerned about dissipation of energies. So the gear is a lossy component in a system where we're trying to get the torque up. If you had a direct drive system, maybe you'd get less torque but go faster. And so this is advantageous to have a gear so that you get more torque but you go slower, versus a direct drive where you typically your windings are wound so that normally the motors rotate fast, and in some applications we just want the output to go slow, so a gear is a necessity in many applications. The other parts for efficiency is the motor winding resistance. So if you're doing 10 amps with 1 ohm, it's 10 amps squared. That's 100 times 1. That's 100 watts lost in 1 ohm if you're at 10 amps. So lower resistance is more efficient. There's limits to how low you can go with your inductance before it looks like a short circuit, but that's another way to increase your efficiency. How much watts you dissipate in the drive is important. So try to keep your efficiencies in the drives at 97% or 99% would be nice. Without superconductor, it's hard to be 100% efficient. But cable, IR drop in cables, things that heat up tend to be inefficient. And when you're coming to a stop, energies are regenerative, and so that tends to charge up the capacitor. Or if you had a battery, you can regen back to the battery. That's That's an efficient way to use energies. Instead of stopping with the brake, you stop with regenerative energies, charging your battery up. And then if you're in an application that someone is back driving the motor, just make sure that you can store all that energy. The rate at which the energy charges onto some battery systems has to be controlled so that you don't heat up the battery. And so there's management for taking regenerative energies and putting it back on the battery. Okay, thanks for watching about gear efficiency.